You are listening to The Vocal Technologist. Spoken tech for your ears.
I nearly skipped this. Thought I knew enough about how we are building software now. I didn't.
Yeah, look, it's entirely understandable. When the baseline tools are changing this rapidly, your first instinct is to just, keep your head down and focus on shipping.
Right, but if you actually poke around the underlying mechanics, we're basically watching the engineering world fracture in real time.
Absolutely.
Because on one hand, you've got this infrastructure operating at a scale that's genuinely hard to comprehend. Like AI models literally optimizing their own runtime environments.
Yep.
And then completely in the other direction, developers are just yanking the emergency brake. They're actively ripping out the newest, shiniest frameworks and retreating to really basic, proven methods.
It's a massive tug of war between capability and maintainability, and I reckon the tension is snapping. The tools themselves are just becoming incredibly dense.
Too dense for most teams, right?
Exactly. Human tolerance for managing that much complexity is just evaporating.
That's what we do here on Vocal Technologist. Pick apart the text so you don't have to. And this tension you just mentioned, this whole fracture between complex automation and the push for simplicity, it's entirely driven by the fact that these new systems are starting to manage themselves.
Right.
We aren't just talking about generating boilerplate code anymore. We're talking about models tweaking their own infrastructure.
Yeah, so take a look at the GPT 5.6 family, specifically the Sol model. The architecture there is heavily focused on fusing frontier intelligence with, frontier efficiency.
Okay, so it's not just about making it smarter.
No, not at all. It was designed from the ground up to handle really aggressive load balancing and caching. So the system can process significantly more tokens without literally melting the servers.
Which sounds like pretty standard server management, right?
Right.
Until you realize the AI is actually involved in the process.
That's the crazy part. GPT 5.6 Sol literally helped optimize its own code execution and resource allocation.
Wait, really?
Yeah, it analyzed the bottlenecks in its own inference layer, and then it suggested architectural tweaks to distribute the processing load more effectively across the GPUs.
I have to admit, I reckon that's a bit of a slippery slope when the code starts tweaking its own dials. I mean, it's impressive, but giving a probabilistic model the keys to its own hardware allocation feels heaps dodgy.
It does sound risky, doesn't it?
Like if it hallucinates a routing rule, does it just take down a whole cluster?
That's the exact fear right there, which is why these agent loops are wrapped in incredibly strict harnesses.
Right.
An agent loop is basically the AI constantly thinking, then acting, and then observing the result in a cycle. But running that cycle for millions of users requires immense compute.
So how do they stop it from eating all the servers?
Well, to make it viable at scale, engineers have broken the loop down across a harness layer, an API layer, and an inference layer. And they use highly specific networking techniques to cut down on all the repetitive overhead.
Give me an example.
So instead of relying on standard HTTP polling, they maintain persistent WebSockets for the agent interactions.
Okay, wait, let me make sure I have the mechanism right here. With standard HTTP polling, the client has to constantly knock on the server's door and ask, do you have an update? Do you have an update?
Exactly.
And every single knock requires a full digital handshake, which obviously costs compute. But WebSockets just open the door once and leave it open.
Spot on. WebSockets keep a bidirectional pipe open, so the server can just push the AI's thoughts to the client the absolute millisecond they're generated.
That makes a lot of sense.
But the optimization goes a lot deeper than just the networking side. They also use these things called stable prompt prefixes.
Right, so I assume a stable prefix means the system prompt, like the rules telling the AI how to behave, it never changes. But how does that actually save them money?
It allows for something called key value caching, or KV caching. When a large language model processes text, it has to convert every single word into mathematical vectors, and then it calculates the attention weights for how each word relates to all the others.
Which is heavy math.
Extremely heavy. If your system prompt is 1,000 words long, doing that math from scratch for every single user query is a colossal waste of GPU cycles.
Because the attention weights for those first 1,000 words are always identical.
Precisely. By keeping that initial context identical, the inference engine can just catch the mathematical state of those first 1,000 words. It skips the math entirely and only calculates the weights for the user's new input.
That's clever.
And you combine that with parallel safety checks, so the security evaluations happen on a separate thread alongside the processing rather than blocking it, and you drastically reduce latency.
It really makes me think about how we delegate tasks to these new agents. It's basically like handing the car keys to a learner driver.
That is a great way to put it.
The level of autonomy you give them depends entirely on the review ease versus the undue cost. Like if you're in an empty paddock, the undue cost is 0. You just let them drive.
Yep. Bump into a fence, no worries.
Exactly. But if you're on the highway, a mistake is catastrophic, so you need your hands hovering right over the wheel.
That's a brilliant framework for it, really. Assessing the cost of rollback is crucial when the agent is making decisions at sub-second speeds. But, this relentless pressure for efficiency isn't just an AI problem. It's fundamentally a human infrastructure problem, too.
Oh, for sure.
Just consider the design choices they had to make over at Canva recently.
Right, because they are operating at an absurd scale. We're talking hundreds of millions of active users.
And every single one of those users has an active session. If a user logs out or changes a password or maybe a security threat is detected, that specific session needs to be revoked instantly.
Right.
Canva was originally managing all these session revocations using an in-memory lookup system based on encrypted browser cookies.
Which makes sense for speed, right? Because storing it in memory is always going to be faster than querying a database on a hard drive.
Well, in a vacuum, yes.
Huh?
But managing an in-memory cache for hundreds of millions of people creates a massive distributed state problem.
How so?
Think about it. When you need to deploy new code, or you just restart a server, you wipe that server's memory.
I see where this is going. When the server comes back online with amnesia, it suddenly has to ask the primary database for millions of revocation records all at once just to rebuild its cache.
Exactly. It creates this massive thundering herd that just hammers the primary database. It basically became a nightmare for their deployment pipeline.
So what do they do?
They migrated to an S3-based caching solution for those revocation records.
Wait, S3? But S3 is just object storage. It's built for storing images and backups. It's not for sub-millisecond caching. Moving from RAM to S3 sounds like a massive downgrade in speed.
It sounds completely counterintuitive, doesn't it?
Yeah, totally.
But the new architecture solved the state problem. By storing the revocation lists as static files in S3 buckets, they completely decoupled the data from the compute nodes.
Oh, I get it. The server's no longer needed to maintain that massive in-memory state.
Exactly. It minimized the localized cache size, sped up deployments because servers could just spin up statelessly, and drastically reduced the load on the primary databases.
It's a really good reminder that optimizing for raw speed on a single machine often just completely breaks down when you try to scale it across a whole fleet.
Absolutely.
Which brings us to the part nobody is talking about out loud. What happens when these automated loops and massive data stores crack open? We're building these highly efficient caching systems. But the persistence of all this data is a huge blind spot.
Oh, the life cycle of conversational data is deeply misunderstood by most developers. Let's take a standard codex interaction, for example.
Okay.
When you chat with a coding assistant, that interaction doesn't just evaporate when you close the window. The entire life of that conversation is written to disk in a journal file as raw JSON.
Wait, so it's not just saving the final code snippet. It's a literal persistent log of every typo, every prompt, every single iteration.
Every single event. And it relies on various background databases as temporary caches and indexes. Your chats are literally logged in a user-specific directory on the server.
Wow.
And the critical piece of engineering here is that this history is maintained even if you archive the conversation in the user interface.
So clicking delete or clear chat on the front end is basically having a lend of me. It's just hiding it from my view, but the JSON log is still sitting on a server somewhere.
Yeah, to actually remove it from the storage infrastructure requires a hard dilution protocol, which most standard user actions just do not trigger. It's just soft deleted, flagged as invisible but waiting to be found.
Which perfectly explains the absolute mess with the Claude leak. Private chats and interactive artifacts literally started showing up in public Google search results.
Yeah, that was a disastrous flaw in the sharing feature. When a user shared a specific artifact, the system manipulated the access control list to make that one specific piece of content public.
Right.
But because everything is logged as a persistent JSON object tied to the broader conversation, a slight misconfiguration in the permissions exposed the surrounding private data too.
And Google's crawlers just indexed a lot. I mean, it was exposing private health records, proprietary source code, personal financial data.
It was bad.
It proves that when you optimize an agent loop by aggressively logging everything as JSON, a single flipped bit in an access control list turns your private data into a public billboard.
It is a profound vulnerability, and it's created entirely by the desire to maintain context for the AI. But, that accidental exposure kind of pales in comparison to the intentional supply chain attacks we're seeing right now.
Oh, yeah.
The DPRK-aligned malware campaign targeting developers is just a masterclass in exploiting modern workflows.
You're talking about the contagious interview campaign.
Oh, yeah. Yes. So North Korean-aligned actors have been posing as recruiters. They hand developers fully functional, complex coding challenge repositories. They even seeded a malicious repository through Elastic's own community Slack channel for job seekers.
Right, so a dev's looking for a job, downloads a repo to do a coding test, completely unaware. But what I don't get is how it evades standard antivirus. Like, if I download a repo with a malicious binary or a heavily obfuscated JavaScript file, my machine usually flags it straight away.
And that is the genius of it. The payload isn't sitting in a regular JavaScript file. It's split into tiny base64 encoded chunks, and those chunks are hidden using steganography inside standard SVG image files.
Images.
Specifically, pictures of flags.
Hold on, they hid a live shell inside a picture of a flag. That is heaps dodgy.
Yeah.
I've seen hackers hide binaries inside the pixels of JPEGs, but how does an SVG actually execute code?
Because an SVG isn't really an image in the traditional sense. It's scalable vector graphics, which is built on XML.
Ah, right. It's just a text file dictating coordinates and shapes.
Exactly. And because it's XML, you can legally embed HTML comments inside it. The attackers just hid the malicious base64 text strings inside standard comment tags within the image code.
And because it's just text sitting inside a comment block of a picture, the antivirus software completely ignores it.
Yep.
But how does the text turn back into a virus?
So when the developer runs standard commands to start the project, like npm run dev or npm start, the project's build scripts execute.
Right.
The attackers modified those build scripts to quietly scan the directory, find the SVG flag images, parse the XML, extract the base64 chunks from the comments, decode them into JavaScript, and then execute them in memory. What lands on the machine is a framework known as the Otter cookie stack.
Okay, so what does Otter Cookie actually do once the image deploys it?
It's a 4-module nightmare. First, it steals browser credentials and crypto wallets.
Naturally.
Second, it does a recursive sweep of your entire local machine, looking for .env files, SSH configurations, AWS credentials, and shell histories.
Wow.
Third, it sets up a clipboard stealer to grab anything you copy and paste. And finally, it opens a socket.io remote access Trojan, giving the attacker a live invisible shell into your machine.
Man, if you're keen on untangling this stuff with us, make sure your notifications are turned on so you catch the next one. But honestly, hearing about Otter Cookie makes me question this whole security narrative.
How so?
Well, we have researchers using the Claude Mythos model to find cryptographic weaknesses, right? They used it to successfully have the key strength of the HAWK digital signature scheme, and they improved attack efficiency on a version of AES by like 800 times. Aren't we just arming the attackers at this point?
It's a highly debated topic, but Anti-Rez, the creator of Redis, made a very compelling argument about this. He pointed out that the primary security risk isn't actually the public release of open-weight models giving tools to script kiddies.
Where's the real danger then?
Inside the advanced AI labs themselves. It's human error and mismanagement during internal model testing. Think about it. When a lab is developing a highly unaligned experimental model capable of breaking advanced encryption, the risk of a severe incident happening locally, before any safety guardrails are even conceived, is immense. Individual companies are simply insufficiently equipped to evaluate the dangers of what they're testing internally in secret.
To be fair to the other side of this argument, with all this invisible complexity malware hiding in pictures, self-optimizing code, AI breaking encryption in secret labs, it makes total sense why so many devs are just hitting the brakes.
Oh, completely.
We're seeing a massive industry-wide pushback for simplicity.
We absolutely are. The cognitive load required to build software right now is just unsustainable. Look at TanStack. They're a huge player in the React ecosystem, and they recently removed React Server Components, or RSC, from their main site architecture.
Which is fascinating because RSC was heavily pushed as the ultimate solution for front-end performance.
I mean, in theory it is. RSC attempts to reduce the amount of JavaScript sent to the client by serializing components on the server and sending them over the wire selectively.
Right.
But TanStack realized the architectural overhead required to manage that serialization and hydration state just wasn't justified.
Let me try an analogy here to see if I have the mechanism straight. It's like a restaurant. Server-side rendering, or SSR, is the chef cooking the entire meal in the kitchen and bringing you the finished plate. It's simple, you just eat it.
Yeah.
But React Server Components is like the chef trying to bring the raw ingredients and a portable stove to your table to finish cooking it in front of you.
That is a great visual.
Sometimes it's a great show, but mostly it's just unnecessary overhead when you just wanted a burger. It's like buying a massive 4WD just to go to the local shops, and they finally traded it back in for a bicycle.
That's spot on. Once TanStack optimized their underlying content renderer, they reverted to that simpler server-side rendering approach and achieved the exact same performance metrics without dragging the store to the table. And Shopify did something very similar.
Right, they overhauled their checkout blocks app, didn't they?
Yes, they transitioned to use Remote DOM and Polaris web components. The entire goal was to shrink bundle sizes, remove heavy dependencies, and improve load times.
Just stripping it back.
Exactly. Lean architecture is the new gold standard. They used AI to help write the transition scripts, sure, but the end result was shedding complexity, not adding it.
It really challenges this prevailing idea that constantly adopting more tooling makes you a better developer. I was reading about that productivity mirage incident that went viral.
Oh, right, the hackathon.
Yeah, a highly prolific former Facebook engineer entered a massive hackathon, and an observer was watching him, expecting to see this crazy setup with all the latest AI autocomplete tools and complex terminal dashboards.
And instead, he was just using a basic, unstyled text editor.
Exactly. He won the entire hackathon using bare-bones tools and raw focus. It basically proved that relying on magical AI generation is entirely secondary to intuition and structural thinking. The quote that stood out to me was, "You don't have to be smart if you can think clearly."
That's a powerful way to frame it.
Because strong engineers systematically evaluate the constraints of a problem. Smart engineers who rely on complex tools often freeze entirely when the tool doesn't have the answer.
And that return to foundational thinking is happening everywhere. Developers are realizing they don't need to fear the core tools they already have. Take the git rebase I command for interactive rebasing.
Oh, man.
It has this long-standing reputation for being terrifying. Like, one wrong keystroke will destroy your entire repository.
I will admit, I've messed up a rebase in the past and lost a whole afternoon trying to untangle the commit history.
You and everyone else. But fundamentally, if you look at the mechanism, it just opens a basic text file. You're simply editing a list of instructions with straightforward verbs like pick, squash, or drop.
Right.
It's a text parser with built-in safety nets. It isn't dark magic, it's just text manipulation. And people are applying that same simplicity to shell scripting too, rediscovering things like the shell colon.
A shell colon is just a null command, isn't it? It literally executes nothing and returns a true exit status.
It does nothing computationally, yeah, but it drastically simplifies error handling and setting default variables through parameter expansion in bash scripts.
That's brilliant.
Using a native tool that does absolutely nothing to make a script safer and infinitely more readable is just the ultimate realization of simplicity.
And it makes you wonder if our engineering metrics for what makes software good are just as broken as our obsession with complex tools. Like, I saw that new research from Embrace regarding Google's core web vitals.
Right, the performance metrics.
Google dictates that a largest contentful paint, or LCP, of 2.5 seconds is the absolute threshold for a good website.
And the LCP metric measures how long it takes for the largest image or text block to become visible on the screen. Google derived that 2.5-second threshold from aggregated data across millions of websites.
Right, but the research from Embrace actually looked at real human behavior across 10 major e-commerce retailers.
Right.
They tracked how load times affected the bounce rate, when people just give up and leave.
And what did they find?
For every single one of those retailers, the bounce rate flatlined between 100 milliseconds and 1 second.
Meaning human patience didn't change at all in that window.
Exactly. But it also means that by the time the site hit Google's official good metric of 2.5 seconds, the bounce rate had already spiked. You'd already lost the customer.
Wow.
4 of those retailers saw their performance plateau well before 2.5 seconds. So Google's official good metric means you have already lost the customer.
Which proves that blindly trusting an aggregated, industry-wide metric instead of observing the actual mechanisms of your specific users just leads to misplaced engineering efforts. You might be spending months of developer time optimizing a caching layer for a metric that has zero tangible business value for your specific context.
But, the quiet part nobody is saying out loud, though, is that even if we want simple software, the underlying models powering the next generation of tools demand serious iron. We can want basic text editors, but the hardware requirements to run localized AI are astronomical.
The raw compute demands are absolutely staggering. But developers are fighting those hardware limits with incredible ingenuity. Look at the Turbo Fieldfare project.
What's that?
It's a custom runtime environment designed specifically to run the Gemma 426B A4B model locally on Apple Silicon Macs.
That is a 26 billion parameter model. Usually you need a massive server rack with dedicated NVIDIA GPUs to even load something that size.
Yes. Normally, running that specific model requires at least 14.3 gigabytes of continuous memory, but Turbo Fieldfare managed to run it using just 2 gigabytes of RAM.
How is that physically possible? You can't compress 14 gigs of neural network weights into 2 gigs of space without destroying the model's intelligence.
Well, you don't compress it, you stream it. They utilized aggressive layer streaming and caching.
Okay, walk me through that.
Instead of loading the entire model into memory at once, the software streams only the specific neural layers it needs from the solid-state drive into the unified memory, computes the math, and instantly discards the layer to make room for the next one.
That is wild.
It's a masterclass in squeezing blood from a stone, utilizing the specific architecture of Apple Silicon to maintain performance while completely starving the system of RAM.
But on the other side of the spectrum, when you get out of local development and look at the data centers, it's all about the absolute brute force approach of raw hardware architecture.
Oh, exactly. When you analyze memory level parallelism, or MLP, AMD is completely dominating the server space right now.
Right.
The biggest bottleneck in AI isn't doing the math, it's fetching the data from memory to feed the processors. AMD is currently pushing 58 concurrent memory requests. Intel's architecture is sitting at 30.
That is a massive difference.
By allowing nearly double the concurrent memory fetches, AMD effectively masks the latency of the hardware, which is absolutely critical for running software at global scale.
It's really wild to think about the historical trajectory here. Back in World War II, the British codebreakers at Bletchley Park were up against the German Tunny cipher, which was significantly more complex than the Enigma machine. So Tommy Flowers built Colossus.
The world's first large-scale programmable electronic digital computer.
Right. And we went from building giant rooms of vacuum tubes and physical paper tape just to crack one critical military code to running a 26 billion parameter AI on a Mac with 2 gigs of RAM just to help us write a web component.
The contrast is staggering, but that exact accessibility, the ability to run highly capable models locally, is why the industry is experiencing what many call the Kubernetes moment for open-weight AI.
Meaning these open models are no longer just experiments, they're becoming the foundational plumbing for the next tech ecosystem.
Precisely. Kubernetes transformed cloud-native computing from a highly bespoke, complex challenge into a standardized, predictable platform. Open-weight AI models are doing the exact same thing right now.
Yep.
To maintain a competitive edge globally, there's a massive push for the U.S. to foster foundational innovation by releasing high-quality open-weight models.
Instead of locking it all behind proprietary APIs.
Exactly, because we are currently obsessed with finding AI that can just write code for us. But when you look at the companies doubling their revenue through AI, the real magic isn't the code.
No.
It's redesigning the workflow and having the deep business context to know what to build in the first place. The tools are basically flawless at this point. Our thinking is the real bottleneck.
So maybe next time you sit down to build, put the AI away for the first 10 minutes and just think it through. Vocal Technologists, see you soon.
Spoken Tech, for your ears.